Welcome to the electronicsHobbyblog.com. This is the first and second of a three-part series on capacitors. In the first part, we'll cover what capacitors are, what they do, and the different types of available capacitors. The second part of this video will discuss capacitors in DC circuits, including both the steady state and transient response. In part 3, we'll take a limited look at capacitors in AC circuits. Each of the installments will include an associated lab segment so that you can see the principles in action. A capacitor is an electronic component that stores energy in the form of an electric charge. Think of it as being similar to a water storage tank. If we fill the tank, we can store the water as long as we like. When we're ready, we can open a valve and use the stored water to run a turbine. Capacitors work in a similar fashion. We can use a voltage source, like a battery, to charge the capacitor. And then, when we need some of the energy back, we can draw from the stored energy inside that capacitor. Unlike resistors, certain types of capacitors are polarized. Electrolytic and tantalum, for example. Polarized capacitors are not tolerant of reverse voltage and will either break down or explode when reverse biased. You'll see that at the end of this segment. Everybody loves that part. Polarized capacitors have their leads clearly marked as to which is the positive and which is the negative. Capacitors are used in all types of circuits. In power supplies, for example, capacitors are used to smooth out AC and to filter out ripple. In audio circuits, capacitors are used both to block DC current, called blocking capacitors, and those are normally used between various stages of an audio amplifier, as well as to filter out noise or to allow the actual audio portion of the signal to bypass certain components, and those are called bypass capacitors. In other circuits, the capacitor's ability to charge and discharge at specific rates is used to generate timing signals, like a clock or a one-time pulse. Don't worry if it seems complicated now. We'll explain it all in short order. In fact, the capacitor is probably the second most used component in electronic circuits, second only to the resistor. Like resistors, capacitors come in many shapes, sizes, and types to satisfy specific needs of a myriad of applications in which they're used. A capacitor is created using two conductive plates with a narrow gap separating them. That gap can be filled with air or with any number of other insulating materials. The insulating material that fills the gap between the plates is called the dielectric. Different dielectrics, along with different manufacturing methods, impart different qualities to the capacitor. Some capacitors are more temperature stable than others. Some have much higher energy storage capacity. Some have lower leakage, more power handling, etc. The value of a capacitor is called the capacitance, and it's measured in farads after Michael Faraday, a British scientist who contributed to the study of electromagnetism and electrochemistry. He discovered the principles that define electromagnetic induction, dimagnetism, and electrolysis. And we'll talk about induction when we talk about coils. Like resistors, capacitors come in a large number of standard values, from very low values in the picofarads, 1 times 10 to the minus 12 farads, to very large values, hundreds of farads. These are called supercapacitors. In fact, supercapacitors can store so much electrical energy that they're often used in place of backup batteries. Larger value capacitors are created by making the plates larger. In general, the larger the capacitance value and/or the voltage tolerance, the larger the physical capacitor. In addition to capacitance value, every capacitor has a voltage rating. It's critically important that you don't exceed the rated voltage or the capacitor could fail. Sometimes capacitors, especially electrolytic ones, will fail short, and that can cause damage to the circuit, so it's really important to keep them within tolerance. Just like with resistors, a capacitor that's stressed beyond its rated value could fail catastrophically and explode. In fact, it's considered a best practice to do what's called derate the capacitor, and that is assume that the stated voltage is just a suggestion. Usually you want at least a 50% safety margin over the stated voltage on the capacitor, just to be safe, especially with electrolytic capacitors. In addition to the rated voltage, capacitors also have a tolerance. Usually it's between 5 and 20%, 20% being the most common. Like resistors, capacitors are marked in a variety of ways, including color bands or dots, numeric and alpha codes, or the value written right on the capacitor. The code system used varies by type of capacitor. For example, electrolytic through-hole capacitors normally have the values written right on the side of the capacitor. Ceramic disc and chip capacitors use a numeric code to indicate the capacitance. It works a lot like resistor codes, where the last digit is the multiplier, and then there's a letter code to indicate the tolerance. There's also codes for voltage rating and temperature coefficient. The temperature coefficient not only gives the rated temperature range, but also defines how the capacitance value changes with temperature. If you're using capacitors for timing circuits, for example, that can be very important because it's going to affect your timing. As hobbyists, though, there are very few applications where we need to factor temperature into a design. But the voltage rating is critical, and we'll always need to consider that. Don't worry if you can't easily read a capacitor's value right away. Like anything else, learning the codes takes some time, and it helps to keep a cheat sheet handy. I also look up the codes on the internet whenever I need to. In fact, like with resistors, there's a number of capacitor value calculators that you can find on the internet. Capacitors are made from a number of different materials and manufacturing methods. Each type of capacitor has specific characteristics, stability, leakage, tolerance, voltage rating, etc. Each type of capacitor offers different benefits and drawbacks that have to be considered based on the application. For example, electrolytic capacitors offer much higher capacitor values for a given size, but also exhibit higher leakage and lower reliability than other types of capacitors. Electrolytic capacitors also tend to fail catastrophically, and they break down over time. In fact, I'm currently restoring a Commodore 128 computer that's about 30 years old, and as part of that restoration, I'll replace all of the electrolytic capacitors just to ensure that they don't fail. When we hook a capacitor up to a battery, current flows through the circuit and the capacitor charges. Current continues to flow until the capacitor is fully charged, and then it stops flowing. A capacitor in its fully charged state blocks DC current. In fact, a capacitor's ability to block DC current has many uses in electronics, and you'll learn about those throughout these lessons. If we quickly disconnect the battery from a charged capacitor, leaving an open circuit, the capacitor will hold its charge indefinitely. Yeah, right. Actually, that's true of a perfect or a theoretical capacitor. But real capacitors exhibit something called leakage. It's like having a very, very high resistor in parallel with the capacitor, so it will slowly leak away that charge. Real capacitors also have something called impedance, which means that they don't necessarily pass current 100% as if they were a short circuit. When they do pass current, they have some resistance. It's very small, probably in the milliohms, and we're not going to worry about it for these lessons, but just understand that no capacitor is perfect, but it's close enough for what we're doing. So now, if we have that capacitor that we've charged, and we put that capacitor into a circuit with a resistance or impedance, the charge will flow out of the capacitor in the form of a current, and the capacitor will discharge until it reaches zero. The rate at which the capacitor charges and discharges is determined by the capacitance, measured in farads, and the resistance of the current path, measured in ohms. And we'll take a look at that in the next section of this video. But first, let's head over to the lab. Here's a few examples of what happens when you reverse bias an electrolytic capacitor. You're going to like this. Everybody loves this part. And everybody who's ever worked in the lab in an electronics class has experienced this before. Wait for it. Wait for it. There we go. There's the magic smoke you've been waiting for. Doesn't smell too good either. It's even more embarrassing when you end up with those little flecks of wax paper stuck all over your face. And here's another, but slightly less catastrophic failure. Same principle, same smoke, same nasty smell. Now let's take a look at some capacitors in DC circuits. In the first part of this video, we discussed what capacitors are, what they do, and the different types of capacitors that are available. At the end of that session, we took a brief look at how capacitors charge and discharge. In this part of the video, we'll take a much deeper look at how they behave in DC circuits, including both transient and steady-state response. You'll recall from our last lesson that when a voltage is applied across a capacitor, current flows and the capacitor charges. Once the capacitor is fully charged, current stops flowing. While the capacitor is charging, the voltage across the capacitor is changing. The current through the capacitor is also changing. To be more specific, the voltage across the capacitor is increasing, and the current through the capacitor is decreasing. During the time these changes are taking place, the capacitor is in a transient state. Its response is changing from one condition to another. Once the capacitor reaches its final fully charged value, which is equal to the voltage applied across the capacitor, then the capacitor is fully charged, and the voltage and the current stop changing. At this point, the voltage and current stay the same. They remain steady, and that's why we call it the steady state. If we apply a voltage across a capacitor circuit, the capacitor starts to charge and continues to charge until it reaches its final voltage. But how quickly does it charge? Or, given the opposite condition, where we put a charged capacitor into a circuit, how quickly does the capacitor discharge? The rate of charge or discharge for a capacitor is a function of the capacitance, we always measure it in farads, and the resistance or impedance of the charge-discharge path, which is always measured in ohms. The formula for the rate of charge or discharge is given by the Greek letter tau is equal to capacitance times resistance. Again, where capacitance is in farads and resistance is in ohms. So, for example, if we had a 100 microfarad capacitor, which is 100 times 10 to the minus sixth, in series with a 100 k ohm resistor, which is 100 times 10 to the sixth, then the rate of charge, tau, is equal to 0.0001 farads times 100,000 ohms, which is 10 seconds. Note that we didn't consider the voltage when we calculated tau. That's because the rate of charge or discharge is independent of the voltage. So how do we determine the voltage across the capacitor over time? Actually, it's fairly simple. By definition, the capacitor charges to 66.6% of the final voltage in tau seconds. It charges 66.6% of the remainder, that would be 33.3 times 66.6%, in 2 times tau, and so on and so forth. Each additional tau, the capacitor charges by an additional 66.6% of whatever the remainder is. So let's look at an example. Let's assume that the capacitor starts out at 0 volts, and the capacitor will eventually charge to 10 volts, the voltage across the circuit. And the way it does that is that in 1 times tau, it charges to 66.66%, right? 2/3 essentially. And that's 6.66 volts in 10 seconds. In 20 seconds, 2 times tau, it charges to 6.66 volts plus the remainder, which is 3.33 volts. It charges up 66.6% of that, so a total is 8.88 volts. In 3 tau, 30 seconds, it charges to 9.63 volts. In 4 tau, it charges to 9.88 volts. And in 5 tau, or 50 seconds, it charges to 9.96 volts. But if the capacitor is only charging by 2/3 of the remainder each time tau passes, tau being 10 seconds in this example, then it can never reach the full 10 volts because it's getting closer and closer, but never quite getting there. And that might be true in theory, but for our engineering purposes, we define the capacitor to be fully charged after 5 tau. So in the example here, where tau is 10 seconds, we define the capacitor to be fully charged at 5 times 10 seconds, or 50 seconds. A capacitor that's discharging works exactly the opposite. It discharges by 66.6%, 2/3, of its value each tau. So using the same capacitor and resistor values as we did in the previous example, and assuming that the capacitor starts out being charged to 10 volts, then we see the following in the discharge. At 1 times tau, or 10 seconds, the capacitor has discharged by 6.66 volts, so the remainder is 3.33 volts. It discharges another 66.6% of the way to 0 in 2 tau, so now the voltage is at 1.11 volts. In 3 tau, or 30 seconds, the voltage is at 0.73 volts. In 4 tau, or 40 seconds, it's at 0.24, and in 5 tau, or 50 seconds, the capacitor is at 0.8 volts. Again, mathematically, the capacitor never actually reaches 0. However, just like with our charge example, we assume the capacitor is fully discharged after 5 tau. So in this example, that would be 50 seconds. So if we looked at the discharge curves for the capacitor in the above examples, the charge and the discharge, they would look like parabolic curves. So they're essentially approaching 0 and approaching the full voltage, which in our case was 10 volts, but they never actually reach it. But remember, for engineering purposes, we assume the capacitor is either fully charged if it's charging or fully discharged if it's discharging at 5 times tau. So that value tau is very important. Let's look at a more complex example. So what if we have more than one resistor? If we have different charge and discharge paths, how will that work? Well, if you take a look at this circuit, you can see that we've got a 100K ohm resistor in series, essentially, with a 50K ohm resistor and a 15 volt source, and a 10 microfarad capacitor across the 50K resistor. So in essence, if you remember our previous lessons, the capacitor is a cross portion of a voltage divider. So we need to figure out what's going to happen in terms of the final voltage across the capacitor. So to do that, what we'll do is we'll assume that the capacitor is an open circuit, because when the capacitor is fully charged, that's how it's going to behave. And if you remember the general formula for a voltage divider, it's going to be R2 over R1 plus R2 times the voltage. So that would be 50K over 150K times 15 volts, or 1/3 times 15 volts. So the voltage across the capacitor is going to be 5 volts. That's what the capacitor will eventually charge to. Once it's fully charged, it'll have 5 volts across it, and it'll behave like an open circuit. When it's charging through the 100K resistor. And so the tau, when it's charging, is equal to 100,000 times 0.00001, or 10 microfarad, 10 times 10 to the minus 6th. So when we close the switch, current flows and the capacitor begins charging. And we can say that it charges to its full value in 5 tau. And tau in this case is 1 second. So 5 seconds to fully charge. If we allow the capacitor to fully charge, and then we open the switch and remove the voltage from the voltage divider, then we basically end up with a circuit that includes just the 5 volt across the capacitor and the 50K ohm resistor. So the tau for discharge is 50,000 ohms times 10 microfarads, which is half a second. So by definition, the capacitor will discharge in 5 tau, or 5 times 0.5 seconds, 2.5 seconds. So here's the oscilloscope screen, and I've got it set to trigger on the rising edge, and it'll do a single trigger, so we'll capture the signal. There we go. And that's exactly what we'd expect to see. Notice how that looks exactly like what we theorized? Let's change it to the negative edge trigger and see what happens when we release the switch. So now we're set for a negative edge trigger. Let's take a look at what happens when I release the switch. And there's the discharge rate. Exactly what we'd expect to see. That same parabolic curve heading towards 0. But what happens when the voltage across the capacitor is continuously changing? We're going to talk about that, along with a little bit of AC theory as it relates to capacitors specifically, in the next installment. Until then, if you like this segment, please like, share, and subscribe. And as always, I really appreciate thoughtful, on-topic comments. Until next time, cheers.